In this question, we see that it talks about the relationship between a K sub P, which is an equilibrium constant in terms of pressures, and a K sub C, which is an equilibrium constant in terms of concentrations. There is an equation that relates these two, and it comes from back in Chem 1, PV equals nRT. You may remember that from the gas chapter, the gas module. Now, because of the relationship, and I'm not going to derive it all, although it is derived in your textbook if you're interested, but because of this relationship, we do see that we can calculate one of these equilibrium constants in terms of the other, and the bottom line is that this is the equation. All right, we have our K sub P is equal to K sub C times the RT, which is exactly the same RT as in our PV equals nRT equation, raised to the delta N power. And the delta N is the change in moles of gas. Again, it comes from the N in the PV equals nRT equation, which stands for the moles of gas. PV equals nRT for a gas. And delta N is the change in the moles of the gas as the reaction proceeds, products minus reactants. So if I'm trying to determine K sub P given Kc, I just simply plug into this equation. You may recall from Chem 1, our R value is the ideal gas constant, which is 0.0821 if we're only going to 3 significant figures. That is a liters, atmospheres over mole Kelvin, but we're not going to worry about units here. All right, the T is the temperature. It does have to be in Kelvin. You cannot plug in a Celsius temperature and get the right answer here. And again, that delta N is the change in moles of gas as the reaction proceeds. So if I just plug into my values, then K sub P equals the value for K sub C, 1.2 times 10 to the third, times my RT, 0.0821, times my temperature in Kelvin. It's already given in Kelvin, 668 Kelvin, all raised to the delta N. Let's go ahead and determine the delta N for this reaction. Delta N, let me write it a little bit neater, is equal to the moles of gas of the products, so that would be 1, because there's a stoichiometric coefficient of 1, minus the moles of gas of reactants. Both of these are gases. There are 2 moles of gas as reactants, so delta N is equal to -1 in this example. Delta N will change depending on what the reaction is. All that I have left is to plug this in my calculator. I'm going to let you punch it in. Make sure that you can punch it in, something raised to the -1, and you should get your answer as 22. Just a note, if you're given the value of Kp and you're trying to calculate Kc, it is this equation, but rearranged, and this is one way to rearrange it, or you can divide by RT raised to the delta N, but of course we know that RT raised to the negative delta N is exactly the same thing as 1 over RT raised to the delta N. That's the way exponents work. And so if you're given Kp and you need to determine Kc, you would still plug into this equation in a similar fashion. So this is an equation you might want to have handy on your equation list as you sit down to do the practice, take the quiz, take the exam.